everybody, my name is Robin and today we are back at Taipei Astronomical Museum, National Science Museum. So this time we're going to check something a bit more astrological, maybe something about Mars, Venus. If you have any problems with or any inquiries about astronomy, you can come to the Astronomical Museum to check it out. There is actually a really good planetarium inside, and you can also learn a lot about planets. You learn how physics works on other planets, their climates, and how Jupiter, what it's made out of, how Venus is this hot, why is Mercury so small, is Pluto considered a planet. You can learn everything here at the Taipei Astronomical Museum, and you can also do a more immersive feeling inside of the museum. Okay, so now let's go inside and take a look at the ticket fees. Just walking inside, as you can see all of these bare structures there. You can see bold structures that basically have an artistic feel, and you can also understand a lot more about astronomy. Over here there's a large tube that gives more sciencey feeling, and there are also some more different types of exhibits about auroras, and tiny little souvenir shop. You can also buy some telescopes from those shops. And over here, this is a balloon, which is the first hot air balloon ever made. This is a model that will actually be lifted up into the air. Over here. After a while, you'll see it fly. Over there. As you can see, this hot air balloon is actually pulled with a few lines, and maybe there is a motor inside. Over here, as you can see, this is the first ever hot air balloon made by Joseph Michael Montgolfier and Jacques Etienne Montgolfier. And basically, this hot air balloon actually is measured 23 meters tall and 15 meters in diameter and weighed approximately 400 kilograms. So after 30 seconds, you can see a small little demonstration of this 400 kilogram hot air balloon actually lifting to the sky. So over here, it actually flew for the first time on November 21st, 1783. And they used paper and cotton to actually create the entire air balloon. They put a few animals on there to test it out, but basically all of those animals passed away. So here, so over here, as you can see, this hot air balloon is actually moving via a cable inside. And over here, look, it's actually moving up as a model demonstration for the first hot air balloon ever made. All right. So over here, this is the lunar probe exhibit. Over here, as you can see, lunar buggy, which you can actually take a picture. So this is more like a model on how the first lunar buggy looked. As you can see, it has the standard stuff, wheels, and basically a steering wheel. But over here, this is more of like a satellite dish that is actually used for connecting to people on Earth. Over here, this is a lunar rover, and this is currently one of the first rovers actually made, and they went on the moon during the Apollo program. So over here, there is also a model of how astronaut suits look like, more of a statue. And over here, there is more like a camera right here. Plus, basically over here, those are NASA's logos and some more scientific-ish stuff. Over here, that's where you actually breathe food. There's food, water, nitrogen, oxygen, and other stuff that you need to have to live. That is more like a life support. Okay. So over here is basically a lunar lander. a model of a lunar lander. Over here. These tiny little thrusters are RCS thrusters. RCS thrusters actually control how the lander actually sits down, basically lands on the moon. So that's what actually creates an accurate landing. So multiple countries have tried doing this. For example, Russia, the USA, Japan, India, and a lot of in China. They all tried landing on the moon before, and some of them succeeded, some of them failed. But because of this competitiveness, we have learned a lot more about the moon and also have different types of rocks being sectioned. So, over here, this is actually a model of the USA's Apollo program's space program. Over here, this is actually a part of a capsule that detached. Normally there would be another capsule inside so that astronauts can go in safely. After a mission, all of these parts will actually be scrapped and left on the moon, and they would just be left to rust. Still, because of these machines, we have learned a lot about the moon, and also have tried ways on how to actually live on the moon. Over here, this is the rocket section of the Taipei Astrology Museum. Over here, this is Japanese H2A rocket made by Mitsubishi, and here is the basically Europe's Arcane 5 ECA by the European Space Agency. Over here, this is a Proton M in 2001 made by Russia. And this is China's Long March to Free Sea, CZ-3C, made by China. Over here, this is made by HALT. And here, this is the Geosynchronous Satellite Launch Vehicle, also called the GSLV, made by India. And lastly, the largest one, the Delta IV Heavy in 2004, made by the USA. So, this one is currently one of the more better rockets here and has actually succeeded in multiple missions. So this is also one of the more classic rockets found by us humans. And we also made this correctly. So, over here. So how do helicopters fly? Moonsford law. Every action force has an equal and opposite reaction force. So, same thing applies to rockets. They actually have oxidizers, igniters, and basically propellant brain and a combustion chamber over here. For example, on the Delta IV Heavy over here, all of these free boosters actually have all of this stuff. And basically, they use different types of fuel. They don't use solid fuel. They actually use liquid fuel. So that means over here, up here, they might need to have a over here they might need an oxidizer, and over here they need fuel injectors, fins, and combustion chambers. Basically, right to the nozzle, moving the entire rocket up. So, once it's in the air, it will actually separate the payload over the rest of the fuel chamber to remove excess weight. So, over here, as you can see, this is the solid propellant rocket anatomy, and this is the liquid propellant rocket's anatomy. This is how a rocket works. So basically, the reaction force is actually higher than the action force, causing the rocket to move up. So basically, here is how it actually works. As a sailboat, right? Basically, there is wind and there is a sail. As you can see over here, once I press this button, the fan will blow the sail over here. Because there's actually the fan actually gets energy to the sail actually moves from the action force, and basically this fan moves from the reaction force right over there. So same for a rocket. Pretend that there is propellant inside of this rocket. Same thing. So the reaction force pushes the rocket up there, and as you can see over here, that's how it moves. So, Currently, we are at the Typhoon exhibit. Over here, this is a simulator which simulates cumulonimbus clouds getting sucked in sucked into a fan, thus creating a typhoon or a tornado. A tornado actually causes some other stuff, and it actually causes severe weather damage and damage to crops as well. Over here, as you can see, this is a steam generator fan. After a while, you will be able to see a model tornado actually appear. So once the steam goes up over here, it will actually simulate a tornado. So now, after we wait, you see there will be a circle-ish cone resembling a tornado or a typhoon. Now, as you see, as the steam goes up, the typhoon comes to life. Over here, this is currently a more accurate resemblance of a typhoon, and over here, as you see, it's all spinning, and yeah. A typhoon is made out of cumulonimbus clouds, will actually create hail or tornado. Basically, tornadoes are similar to typhoons. They basically have violent winds and basically hundreds of kilometers in diameter. So over here, this is just a small little resemblance of a typhoon. Yeah. Over here, we're at the Earth's structure. Over here at this exhibit, you can actually learn a lot about Earth's structure. Over here, the Earth can be divided into 3 layers: a core, mantle, and crust. Over here, we are living at the crust, as we can understand. We won't be able to bear the heat inside of the mantle and the core. So the core is actually basically over here. We live at the crust. Over here is where you can get fossil fuels and some other minerals. Over here, the Mohorsic, this continuity, actually connects the crust with the upper mantle. The upper mantle is already heated enough. It has mostly some other minerals and they're mostly melted. Over here, after the transition zone, we go to the lower mantle where there are mostly lava and some other precious metals melted inside. And after the Gutenberg discontinuity, you can actually arrive at the outer core, the hottest part of the Earth, and the most boiling place. Fully lava, all melted metals. If you touch it, your hand will actually burn. Inside, the last part and the middle of the Earth is the inner core. The inner core is the hottest part of the Earth, and has basically is the current center of the Earth. So over here, as we can see, there is a simulator over here. So over here, this is the mantle. The mantle is, as I said before, basically made out of melted minerals. And over here, outer core. The outer core is basically melted metals, but not as hot as the inner. The inner core is the hottest, most burning part of the entire Earth. So, the last part is the Earth crust. The crust is cool and basically not hot. You can find fossil fuels, important minerals, diamonds, and as long as it's made in intense pressure, you can find it in the crust. So, over here, as you can see, this is Earth's magnetic field. Over here, this is the geomagnetic North Pole. And over here, the geographic North Pole is actually completely different from the geomagnetic North Pole because the Earth's magnetic field is kind of different. The mechanism by which the Earth generates a magnetic field is known as a dynamo. The Earth's magnetic field is believed to be created by the rotation of Earth's liquid iron ore, as we said before, in the core. As I said before, it's all melted metals and lava. So, geomagnetic reversal refers to a change basically a change in Earth's magnetic field. During reversal, the magnetic field weakens until the positions of the magnetic poles switch over a period of 1,000 years. The most recent reversal occurred around 780,000 years ago. So, basically, after a while, the geomagnetic pole will actually switch sides. They'll keep switching. And yeah, as we've said before in typhoons, this is actually a small little typhoon. Okay. This is the geomagnetic polarity during the last 4 million years. So, over here, this is basically normal, but over here, in these time periods, they're reversed. And here is as you can see. This is a graphic on how the geomagnetic poles actually reversed. So over here, early astronauts actually had to use different types of tubular food to actually survive, because in zero gravity environments, everything will float. So they have to grow their own stuff, and everything has to be micros. So over here, this is how they grow food in a zero gravity environment. And over here, these are vacuum foods that reduce crumbled stuff, toothpaste foods. And yes, they're highly nutritious, small inside, and yeah, they have a lot of different flavors. Over here is, some jelly beans, some biscuits, and nuts. They have to be completely, they shouldn't have any crumbled stuff. They shouldn't have any crumbs, and or else those crumbs will actually interfere with the space station's how should I say this? Machinery, and reduce the accuracy of them. Over here, this is how they grow plants. They use soft cotton to actually make these plants grow roots inside, and they will also spray some nutritious fluids inside. Over here. Now you're wondering, once they're done with space food, do they have a space toilet? Yes, they do. So, something really disgusting. When you're an astronaut and you have to poop, you have to squeeze yourself in the space toilet, and your poop will actually be sent back to Earth. Absolutely disgusting, I know. And plus, something even more disgusting, when you're pee, your urine turns into drinking water. You actually can only drink your own urine. So over here, these are chronicle filters, and they sanitate your urine so that it can actually turn into normal drinking water. So over here, this exhibit is about the rotation speed of spiral galaxies. So over here, there is rigid body rotation, which basically means that all of the celestial bodies will move together. So basically, some people think that the spiral galaxies are supposed to move in a rigid body rotation. So as you can see over here on this tiny little dynamic, rigid body rotations basically move together. So then there is something else made by Kepler. This is Kepler's theory on rotation. So over here, Kepler thinks that the one near the sun, or a black hole, basically anything with mass, will actually spin the fastest. Meanwhile, the one furthest from the black hole or sun will be the slowest. This is Kepler's rotation, and as you can see over here, takes quite a lot of time. This demonstration actually talks about Kepler's rotation. Once we wait until the demographic is done, why don't we learn something about Kepler's law? So, if the mass of the galaxy is concentrated at its center, the galaxy's rotational speed should decrease from the center to the edge, according to Kepler's law. But still, remember, this demographic isn't 100% correct. Kepler's law is actually somewhat wrong. Same for the rigid body rotation, because the rigid body rotation is actually said by astronomer Vera Rubin. So, but in recent studies, it's shown that it's wrong. So, actual observations are quite different, but we still have to wait. So, why don't we take a look over here? So, this is Kepler's law, and yeah, basically they think that the rotation of spiral galaxies is kind of like this. They circulate around the center of the galaxy. Over here, you can see the demo that the furthest planet will actually stay the slowest, and yeah. Over here, this is Kepler's law. Now, what about the actual observations? In actual observations, they're quite different from Kepler's law, as it is not this correct. So over here, I mean, yeah, they will still be quite different. Okay. So basically, observational results show that the orbital speeds of stars in the Milky Way won't fit this law. Scientists have concluded that the addition to observable celestial bodies, basically invisible dark matter, also affect the movement of celestial bodies. So, Kepler's law is half correct. Because if there weren't any dark matter inside the Milky Way, which is nearly impossible, basically this will actually happen. So, over here in these pictures, you can see a lot of different types of galaxies. And yeah, quite beautiful. So, yeah, again, maybe if you can, maybe you can see Andromeda or Milky Way. Yeah, right. So, the Kepler rotation is almost done. Over here, as you can see, this is an armillary sphere. An armillary sphere is actually used to observe stars and measure their coordinates at night, and basically measure the position of the sun during the day. Over here is an actual model of an armillary. You can see they are made of a few spheres to actually understand where the sun is positioned. This is quite an engineering marvel made by ancient China during the Ming Dynasty. But after a while, a few astronomers chose to actually simplify it and choose to turn it into a bridge armilla. And a bridge armilla is actually just a simplified version of the armillary sphere. They're both currently kept at the Purple Mountain Observatory in Nanjing as a piece of cultural heritage. Now that we understand what the armillary sphere is, how do we understand also about the sextant? Sextant is a reflective optical instrument made by the British to determine the observer's position by measuring the angle between two objects. It can achieve an accuracy of up to 10 arcsecs, and it's used for memory and positioning. As you can see over here, this painting of Johannes and Elizabeth Hevelius observing with the sextant. Okay, now over here, as you can see, this is currently a model of a sextant, and as you can see, basically, normally there will be a telescope over here, an index mirror, horizon mirror, glass filter, another horizon mirror, a small mirror over here on the small mirror, and an index arm, which we have over here. We would also have a drum, and over here, the viewer has to look through the telescope first, and then out the basically all of the poles of the stars' location. Over here, we are currently at the radio telescope exhibit. Over here, basically, radio waves are the longest waves in the electromagnetic spectrum. Image resolution and wavelength are inversely proportional. And over here, as you can see, this is the VLA, the Very Large Array of basically radio antennas. These radio antennas are actually radio telescopes. Over here is a model of how the Very Large Array works. As you can see, they will actually slowly go together to focus on one subject. And this is actually how the Very Large Array works. Very great model to look at. And over here, they use interferometry or interferometry to enhance resolution. Astronomers use interferometric methods by combining smaller radio antennae to simulate a large single-dish antenna, as you can see on the Very Large Array and the model. This model actually portrays how all of these small antennas can actually be used as one huge antenna. Over here, after a while, you will see how this entire array actually works. No, over here, it focuses on one single direction. It basically turns into an extremely large radio telescope, and it's actually quite a great technology to look at. So, yeah. So, in this universe, are there any types of intelligent life forms here? So, maybe there will be. So, how can we actually do that? With Professor Drake's equation to calculate the possibility of advanced civilizations, you can see over here. So, N equals R times Fp times Ne times Fl times Fi times Fc times L. So, N equals the number of civilizations with which communication might be possible. R is the average number of stars created per year. Fp is a fraction of stars that have planets. Ne is the average number of planets that are in habitable zones. Fl is the fraction of the above that can develop life. Fi is the fraction of the above that can develop intelligent life. Fc is a fraction of the above that can develop remote communication abilities. And L is the length of time the above civilizations could last. So, over here, maybe you can actually find out, with this equation, maybe you can find out if aliens actually exist. So, over here, people have tried using radio signals and to try and find aliens. So, over here, they found the wow signal. People still don't know how this signal actually appeared. So, alright, over here, some interactive interfaces with the wow signal and the search for alien radio signals. Okay, so yeah. So over here, these are gravitational waves. In Einstein's theory of general relativity, gravity can be expressed as the curvature of space and time produced by mass. So over here inside, we have a tiny little video to show you guys. So, when an object of mass accelerates, it destroys space-time and a water drop creating ripples on the surface of a lake. So, for example, when two black holes basically continuously change, the orbiting black holes will continuously change the curvature, and they ripple in space-time in gravitational waves. So, thanks to the changes in space, resulting from gravitational waves using measurements made by laser interferometers. So these are laser interferometers, and this is a concept from the LEGO experiment, using two laser interferometers with two 4-kilometer long tunnels, and it can prove the existence of actual gravitational waves. They have no relevance. So now, this is the sound of a gravitational wave. That is the sound. Great, perfect. Now